My team member is Pham, Pham, and Nguyen. Want me to start over again? Okay. Good afternoon. My name is Anh-Vo Nguyen. My team members are Pham, and Nguyen. The title of our project is FPGA Integrated Sensor Node. We call it PRISM 493 for short. Okay. Our goal is intended to, as proof of concept, demonstrating that an FPGA is capable of implementing the processes of a sensor node, such that it can achieve higher performance and reduce communication traffic and power consumption. The reason for that is, as assistant sensor nodes are extendable to carry out added functionality, there's a bottleneck in the processes, and it's due to the microcontroller. And it's mostly due to the software process, why one software procedures wait for the other to be executed. So what is a wireless sensor network? It's a system of individual sensor nodes, and they combine to transmit and evaluate and transmit data through the network back to the base station. And basically it evaluates physical characteristics of its local environment within the mesh network. And with this capability, there's a variety of applications it can be used for, among them weather forecasting, battlefield surveillance, and enemy tracking. Right. So a typical sensor node consists of a microprocessor, wireless transceiver, and sensors. And its main function is to collect data from the sensors and communicate those data back to other nodes and relay it back to the base station. Okay. For our projects, our goal is to redesign the architecture of the existing sensor node. And basically it's pretty much nearly identical to the existing one. It still has the radio stack circuitry, the ADC functionality with the sensors, and require flash memory to run the software program. But the difference is we will implement a soft processor core in the FPGA to act as the host controller. But since the FPGA doesn't have an internal ADC capability as the microcontroller, we added an ADC chip on it as well. Okay. And there's some trade-off between the microprocessor and FPGA-driven sensor nodes. Cost right now for microprocessors is cheaper, but now with the popularity of the FPGA, cost is catching up. Initial design of the FPGA integrated sensor node, it's more complex, but once it's implemented, the ease of you want to make changes to it, it's a lot simpler. For customizability, for microprocessor, you can only do it via software. But as for FPGA, as you can see, you can do both via software and hardware. So, hence with that capability, the time to market for the configuration is faster for the FPGA. Okay. Next up, with Pham, we're going to talk about the hardware design.
Now I'm going to talk about hardware design. For our project, there are some major components to be selected based on the requirements, such as the Intel Victor Nano AGL250 FPGA was selected because it's low cost and low power. The CC1000 transceiver was chosen to communicate with the existing sensor node at 950 MHz, and it requires 3 volt power supply. The ADC LTC 180L were picked out because it's also a low power consumption device, and it has sleep mode. And the rest of our active components are the voltage regulator, LP3992, the photo sensor, and temperature sensor. This is our schematic of the whole circuit. As you can see, this is the CC1000 circuit chip. It requires 3 volts to operate, and this pin right here to connect to interface with the FPGA. Down here is the ADC we take the analog signal from the photo sensor and the light sensor, and then convert them to a digital data, and then use it for pins to transfer to the FPGA. This is our preliminary PCB layout of the whole circuit on 2 layers. Since we are running out of time and not familiar with laying out the PCB IF circuit, we have decided to redesign our whole system. And our new system consists of the FPGA evaluation kit and the CC1000 PP 915 module and the PCB layout of the power and the ADC circuit on it. As you can see, this is the CC1000 PP module. This is prototype board and is ideal to replace the transceiver circuitry of our original design. And this is the PCB layout of the ADC and power circuit. And this the actual PCB board of the ADC and the power. Lastly, this is our final hardware integration with every component. You can see this is CC 1000 PP, the ADC, PCB board, and the FPGA evaluation kit connected together. And next, Sean will talk about FPGA development.